Uh, we are just approaching almost the end of discussion on Hardy-Weinberg principle. Today would be part 3, where we will try to understand how to solve some problems connected to genetics which would follow Hardy-Weinberg principle or Hardy-Weinberg equilibrium or Hardy-Weinberg law. Now let us repeat again the interpretation of the law. It only says allele frequency will be constant and genotype frequency will be constant in a population. This is important. Both the allele and genotype will be a constant when population is large, there is no mutation there, and no migration happens in that particular population, and no natural selection, but there will be no particularly the mating in random. The random mating should happen in the random, and then there should be no natural selection, no migration, and no mutation, and the population should be very large. In that condition, the Hardy-Weinberg principle works, which will indicate in that particular type of a geographic area and a population, allele frequency will be constant generation after generation. Similarly, genotype frequency will be constant, will be in equilibrium over many generations. So both allele and genotype equilibrium is maintained when the conditions are followed. Now these two equations you must remember to solve the problems. One is P plus Q, that would give us the frequency of allele. When you take P plus Q as a sum is equal to 1, and frequency of allele can be calculated. When you say P plus Q is equal to 1, P or Q will become decimals. It cannot be more than that. P cannot be 1 plus Q cannot be 0, because those two frequencies will be there in a population. P refers to the dominant and Q refers to the allele. Every organism, every individual in a population which is diploid in number must have two alleles. Maybe two of them may be dominant or two of them may be recessive. As the second equation tells, P plus Q square is equal to, if you write that will be P square plus 2PQ plus Q square is equal to 1. So when you say P square, that is a diploid. There will be two alleles. The two alleles will be dominant or it may be recessive. 2PQ refers to the recurrence of the when the meiosis takes place, there will be one part of the parent will come to one of the zygote, other part will come to the other zygote, like that. There will be separation or segregation. That follows the law of Mendel. So these two laws we should be able to remember. Now, the allele frequency and the genotype frequency, these two can be expressed in fraction form. We can use it in a fraction form as I have given here. P is equal to 6 on 10 is a fraction form. In this, P refers to the frequency of the dominant gene. So it says that dominant gene the frequency will be 6 in a population of 10. Now, second one, either allele type or genotype frequency can be expressed in the decimal form also. And also we can express that in the percentage form. If these three terms are remembered by you, that will solve a large number of problems. I am telling this because CBZ students normally do not have that amount of knowledge on the mathematical issues, even including me. I am a pure biologist. It will be very difficult for me to do any statistical activity, but you are all young and you have gone to PCMB, therefore you should be in a position to follow this very clearly. In other words, I will repeat that the frequency of allele or genotype can be expressed in fraction, can be expressed in decimal form, can be expressed in percentage, or in all the three forms. We will take one example here. In the equation P plus Q, I have written P refers to, I told you, an allele which is dominant over the allele Q. We are talking of only one here. When you say P square, it becomes 2. Q square becomes 2. So here we are talking of only one. If you feel that is equal to 1, that is a constant, then let us assume that in this particular thing I have shown the decimal form, sorry, fraction form. I have shown here the P allele will appear 6 times in a population of 10. The same thing can be written in the form of decimal. That becomes 0.6. So the frequency of the allele P will be 0.6 in a population of 10. Or if you want to express that in terms of a percentage, 60% of the population in a 100 will be P, or it will be dominant. If you look at Q now, Q will be recessive allele. Recessive allele will be 4. Why it is 4? That will be, if it is 10, you equal to 6 minus Q. So 10 is equal to 6 plus Q. So equals to now 6 plus 4. So this 4 is the Q represented in the diagram. This will be full form. If you want to make it in the decimal form, it will be PQ is equal to 0.6 and 0.4 equal to 1. So that will be 10 and 4 in the fraction form, 0.4 in the decimal form, 40% in the percentage form. So if you remember these things, some of the sums what you come across may be useful to you. Now let's take up one more example here. In this example, phenotype is given. Phenotype refers to the appearance is given, and then population size is given. When you say population size, it will be a number. It may be infinite or it may be any number, but in this case we have taken as an example 497 would be the number of in a population. This we are talking of a plant population, in that there will be red flowers. That is the phenotype of the flower. The flowers will be red in color. Their number will be 452. When you say red flower, and when you are talking of the phenotype, we are talking of the individual here with 2 alleles in that. 2 alleles in that. So that will be homozygous in case of this red flower. That homozygous will be written in the form of, since it is dominant one, we will say it will be RR, that is the genotype. And then the second type of the observation is there will be red flowers, which will be, number will be 43, but these are heterozygous, that is the genotype. When you say heterozygous, it contains both the types of alleles, both the allele, one for dominant, one for recessive allele will be there in that particular organism, but that flowers appears red because of the dominant R. You remember the Mendel's law, dominant gene, even if there is one allele, will express in the phenotype. So the phenotype will be red flower, but the genotype will be RR. This is the genotype. So genotype will be one allele R for dominant, one allele for R for white color. Now the third one we get observation is white flowers. White flowers appear white in color, and that will number be 2, and that is homozygous. It can appear white only when it is in the homozygous form. If it is in the heterozygous form, it will be expressed by the dominant allele. Therefore, when you think of the homozygous, that will be white in color, and that is that the genotype is represented by small r of the lower case of the alphabet, or r. So that is the expression. So now we know the total number of population size is 497. In that, the red variety, which is homozygous, is 452. When you work out, that comes to 90.95% if you want to express that. Or if you want to calculate that in terms of decimal, it comes to 0.909. So we can express these things in 3 different say notations. It may be fraction, it may be decimal, it may be percentage. Now coming to the heterozygous type, there are 43 numbers in the population, and if you take the total number of population and divide it by 43, you get the decimal number. That will be 0.87 will be heterozygous, or we can say 8.65% will be heterozygous. And then coming to white, there are only 2. Easily we can count them. Even if you get only one of these number, you can work out all these things. Because homozygous white is only 2, you can count them, and the phenotype is white. Because it becomes white flower, then it should be recessive allele, 2 doses must be there, 2 alleles must be there. The allele pair will be representing the recessive type, and that will be 0.044 in decimal, or 0.40% in percentage. So that's how it can be expressed. Now, when you want to, if you want to say, once again I will repeat that, if you want to express the genotype of the red flowers, genotype of the red flower, that will be 0.909 in decimals. If you want to express that in the percentage, it will be 90.95% will be red dominant. If you want to go to heterozygous, take the number given and then divide it by total number. That will give you the percentage and also the decimal number. And similarly, take the given number, that is the phenotype number is 2, and the 2 also is the heterozygous, the homozygous type, homozygous white, and if you divide by that, you will get the number here, that is the in decimals, and that will be in percentage. Now, after understanding that, if you add all these things, 90.95, 8.65 and 0.04, you get 100%. That means the equilibrium is working in this particular case. The HARDY-WEINBERG principle is true applied to this particular example given. If you want to express the, now we express the genotype. If you want to express the allele frequency, we will go for that. Allele frequency of R. R represents one of the allele here. Now, when you say genotype, we are taking the diploid number. So when you take up only one R, that will be haploid, that is one allele you have to talk. Therefore, you take the square root of this 909. That will give you the frequency of one allele, that will be 0.953, or in percentage it will be 95.3. Similarly, if you take for the allele, that is the recessive allele, which will be represented by the frequency of the recessive allele in the population of 197 will be the square root of the genotype, and that will be 0.47 or 4.7%. So when you add up 95.3 plus 4.7, you get 100. So in this case also the Hardy-Weinberg principle is working. So this is how the frequency is expressed. Frequency refers to the number of individuals in a given population, or how many times the given gene will appear in the population. Either single gene, or you can take the individual of the diploid gene, that will give the numbers. So this law can be applied. What we do, we will try to know one or two simple examples so that you will understand how you can work out some problems. As I said earlier, you are all students of mathematics and physics. You are in a better position to understand these equations, and it will help you a lot if you learn one or two more examples. Thank you.